Alysson Vrielink, and I am working with the superconducting radio frequency group at Triumph. Today I'm going to be talking to you about an RF deflecting cavity that is being designed for aerial E-limit bunch length measurements. So we'll start off with a background on the aerial E-limit project, what it is, and why do we need a deflecting cavity. I will talk about what a deflecting cavity is, how it works, and how we built it using RF simulations and particle dynamics. And then we'll look at how these parameters were experimentally verified. And I'll focus a lot on beamline integration, which is happening right now between beam-loaded testing as well as developing a user interface that will allow for easy measurement of the bunch length. So, starting off with the aerial E-limit project. This is a really exciting new facility being developed at Triumph right now. It's going to advance research in fields ranging from high-end physics to materials engineering, and of course we're going to be using it for the production of crucial medical isotopes. As an accelerator engineer, what's exciting for me is the 1.3 gigahertz superconducting technology, and it's going to be a 50 MeV, 10 milliamp electron linear accelerator. So on the picture on the left here, we can actually see the injection line. This is where it all starts. This is where the electrons are accelerated to relativistic speeds, which are necessary for efficient acceleration further along when we get to the superconducting technology. So it starts off with a 100 kV electron gun, and the beam will then go through the beam line, and there's an option either to go straight through to where the accelerating modules are going to be, or you can turn the magnet on there, in green, and it'll go through this 90-degree angle. Now, why do we need an analyzing leg? Well, several people at this conference are talking about projects that they're doing that require beam. And anyone that's used beam knows that they want a good quality beam. You want something that's bright, you want something that has good resolution in the time domain and space domain. So we have to take a look at these things. We look at things like the cross-sectional area of the beam, the current, and one of the things we want to know is how is the beam distributed in the time domain. Now, this is tricky because we're looking at bunches. So the beam is bunched into bunches of electrons, and these bunches can be like on the order of a couple of picoseconds. So you need something with femtosecond resolution, and that's expensive and hard to procure. But another way we can do this is we don't have to look at it in the time domain. If we can find something that maps our beam from the time domain to the spatial domain, then we can get the information in the space domain. And it's really easy for us to look at things like the area of the beam in the space domain. In fact, all of those blue rectangles are position measurements. So that's actually where the deflecting cavity comes in. You can see it, it's a green box there on the analyzing leg. And what this device does is, depending on the time of arrival of an electron, it will deflect it by a different amount. And using this method, we can actually look at the spread in the beam in the time domain and get it in the y direction after the deflecting cavity. So how does this work? Well, going back to the basics, the deflecting cavity is a resonant cavity. And what we do to solve for the electric and magnetic fields is we'll apply boundary conditions on the cavity geometry. And this cavity is made out of copper. There's actually a cross-sectional view of it on the left there. And we apply boundary conditions and then we solve for the electric and magnetic fields. Now, several modes will actually propagate. You get these standing waves as your solution. And we can use the mode that has an electric field in the y direction and a magnetic field in the z direction. And what this will give us is a net deflection of an electron that goes through this cavity in the y direction. And you can actually see some RF simulations we did. You can see on the top left there, you have the electric field going up, y direction, and then top right, you have a magnetic field going in the x direction. As I said, you'll have other modes propagating. These will propagate at different frequencies. So I just showed you on the bottom there's some other modes that will propagate. We want to operate at the 1.3 gigahertz resonant frequency. So I mentioned that we need to solve for the electromagnetic fields. Now, if any of you have taken a course on ENAC, you know it's not that simple to analytically solve for these. And in fact, with this complicated of a geometry, it's impossible. So instead what we do is we use RF simulation software. For this project, we use CST Micro Studios. And here's the output from one of our simulations that shows the on-axis fields. So you can see we've got a magnetic field and the electric field, and these are standing waves. But keep in mind relativistic kinematics and the Lorentz force. And we can see this plot here shows us very clearly that depending on the phase offset of our deflecting cavity, you're going to see a different amount of deflection. This is where the mapping comes in. The deflection in the y direction depends on the phase of the RF fields when the electron reaches the cavity. So now we have a device that's going to do what we want. We need to make sure it does this efficiently. And that's when we look at some other characteristics. In particular, some things we want to know are, we want to know the resonant frequency, and we want to make sure that our cavity is at that frequency. Because if you're not driving your cavity at the resonant frequency, it's going to require much more power to operate. We also want to know the geometry factor. And this tells us the relationship between how much power do I need in my cavity to get the fields that I need to produce the deflection that I want. So say I want to have an electron deflected by 20 millimeters at the end, way more than we